SwayamPrabha. Digital India. Educated India.
Hello everyone. So, we are discussing the removal of water pollution by textile material. So, heavy metal is very harmful for human health. So, textile material is used to remove the heavy metal from water by functionalization of the fiber. So, functional fibers are used to remove the heavy metals and which protect us from any different diseases. So, the chemical reaction is known as chelation reaction. The chelation reaction is that basically it is a chemical process where one chelating agent is used which binds the basically to a central metal ion at two or more points. So, that is a important thing. You can see here the red color particles, it is a chelating agent, okay. And where it binds the metal ions. So, here this dots black positive signs are it is a these are a metallic ion, the positive ion, and they actually they are attached in two or more points, different points they are joining, which form a stable ring like coordination system. So, you can see this is a chelating agent. So, which is known as ion exchange particle, and here the metal ions, these are the different metal ions are there, they get attached with this at different point, maybe more two or more points, and which makes a stable ring like coordination. So, it will form a ring like coordination. Okay. So, these particles they become larger, okay, and this complex is they form a stable complex. So, this chelating agent are compound that forms a stable ring like complex with metal ions. So, this is the metal ions which are present in the water as pollutant, they form this compound and trap this metal ions. Okay. So, this they are trapping them to prevent unwanted chemical reaction, oxidation or toxicity enhancement. So, they actually form a compound and then they make the this ion inactivate. So, that is that this ion this metal ions will not actually this cation, this metal ions they do not they are chemically becoming inactive. So, they do not do any other reactions. Now, this is a typical chelation reaction. So, here removal efficiency of this metal ion is more than 90% depending on the type of this treatment the activation, how the fibers are activated with the this chelating agent. So, this functional group. So, what are the functional group we use? We can select different functional group that enhance the ion binding. So, with this chelating agent there are different functional groups are there, and which actually bonds form bonds. So, this is effective for water purification, particularly for heavy metals. So, the water with heavy metal can be actually removed by this type of reaction, and this material is actually the fiber surface is activated with this chelating agent. So, next treatment is that we can actually modify the textile surface by plasma treatment. Maybe we can treat the fiber, we can modify the fiber surface or even fabric surface. So, by doing plasma treatment, so we can change the surface so that it can remove the dye from wastewater. The dye can get adsorbed on the surface. The removal efficiency is R C0 minus Ct by C0 expressed in percent. What is C0 is concentration of, so input dye. So, textile membranes are used to remove the azo dye, which is harmful for human health. So, these azo dyes are removed. So, this adsorption enhanced surface by the surface charge, because the plasma treatment increase the surface charge, and this azo dye are adsorbed in the surface. So, this adsorption increases by the plasma treatment. So, for textile effluent treatment where azo dyes are used, so that type of application. So, we can use this type of material. And next is the layer by layer deposition of nanomembrane. So, nanofiber water filtration membrane we can use. So, by the layer by layer deposition. So, here we can see polymer we use, then solvent and nanoparticles here. So, this solution we use stirring to have proper solution of nanoparticle, and so that coagulation does not take place, it is uniform solution. So, finally, we get viscous polymer solution along with the nanoparticles there, okay. And that we use the electrospinning here. So, syringe pump is there, and high voltage we apply in the, this is the syringe, and here high voltage we apply to have the this nanofiber, electrospun nanofiber, which is deposited on the some substrate, and here you can see the nanofiber. So, nanofiber we produce here, and with the even nanoparticles incorporated here. So, here the surface area is very high, 100 square meter per gram of fiber of this membrane. So, here we can have high water flow rate, water flux 100 to 1000 liter per square meter area per hour, and it removes the microorganism because and also colloids it removes because of the very nano level structural opening. So, pore size is very fine, and it provides high permeability. So, due to the porous structure it provides high permeability, but at the same time it can restrict the, it can remove the microorganism or even colloids it removes. So, here we will see that in situ how we can form the nanoparticles. There is a process. So, by photocatalytic textile membrane we use. So, this photocatalytic textile membranes are used for water filtration, and titanium dioxide photocatalysis is the process you can see which forms the membrane. So, this is the relation equation here. It generates a reactive oxygen species, and as this reactive oxygen species is there which degrades the organic pollutants by chemical reaction, and it provides self cleaning filtration. Next is the graphene based textile filter, which is used for both air and water filtration. So, here you can see the graphene oxide, this is the graphene oxide dispersion we use in two process we can adopt. One is reduction in fabric stage. So, that we can do, and also we can do reduction in the dispersion stage. So, graphene oxide is a single atomic layered material derived from the chemical oxidation of graphite, and which is characterized by the high oxygen content. So, hydroxyl, epoxyl, there is carboxyl groups are there, and hydrophilic nature that enables aqueous dispersion. So, these are hydrophilic in nature also. So, you can see the two processes where the fabric is there, okay, and the fabric is coated with the graphene oxide dispersion. So, this fabric is coated, this is the coated base fabric, and then the reduction is carried out at this stage after coating. This is one way, and also we can use the first reduction we do, then we coat the on the fabric. So, reduction of graphene is done at initially, then it is the this dispersion is then coated with the dispersion is coated on the fabric surface. So, both the processes are adopted. So, here you can see the theoretical surface area is around 2600 square meter per gram, very high surface area, strong adsorption of organic pollutants. So, this graphene actually due to its very high surface area, and it adsorbs the organic pollutant from water used in advanced filtration system. So, if we want to remove the organic component, so that organic pollutant, so in advanced textile filter, we use this type of graphene treated textile filter. So, due to its the presence of graphite, so this is a highly electrical conductive. So, we can use in this type of applications. We can produce the carbon nanotube membranes also. So, carbon nanotube diameter is 1 to 50 nanometer, high mechanical strength, and fast water transport through nanochannels. So, that is advantage of carbon nanotube. So, it does not actually restrict the water flow. So, high performance membrane we can use. So, we have studied on the carbon nanotube or carbon nano rod we have used how to and this carbon nanotube is widely used for textile, that is textile material. Also we can modify the surface for improving the adsorption capacity. We can basically coat the surface, we can use the nanotechnology for surface modification, we can use biotreatment for surface modification, we can incorporate the hydrophobicity to improve the adsorption capacity, we can change the adsorption capacity, we can functionalize the fiber surface or fabric surface. Plasma treatment, as we have already discussed, by chemical treatment we can modify the surface of textile fibers. So, we can modify in many ways and we use this modified fiber for different applications. So, plasma treatment, what it does during plasma treatment, it introduces functional groove. So, OH and COOH group it introduces on the fiber surface and which enhance the surface activity. So, what it does? It improves the surface energy and weightability of fiber, because OH group has come. So, it will make the fiber weightable. So, if we increase the hydrophilicity, we can use the plasma treatment. So, it enhance the adsorption of pollutants or catalytic activity. So, we can have enhance the adsorption capacity by surface treatment. The plasma power typically 10 to 100 watt for textile treatment. So, at that watt we can treat the textile material. So, coating, if you see, the sol gel coating is used for coating the textile material. In sol gel process forms metal oxide by which coats the titanium dioxide or silicon oxide on the fiber. So, TiO2 or SiO2, it is actually this metal oxide is formed which coats the fiber. The hydrolysis reaction is given by, this is the hydrolysis reaction. So, this produces thin porous coating on the fiber on the fabric, porous coating thin, and which improves the filtration activity. So, sol gel coating is done on textile material to improve the filtration, because it forms a porous coat on the textile material. So, it enhances the chemical resistivity of textile membrane, because due to this coating the fibers are protected. So, chemical resistance of this membrane, it is enhanced, and smart textiles are used for water filtration. So, we can use integration of sensor for monitoring, pollutant monitoring. We can incorporate different types of sensor within the textile material, and which sense the what are the type of pollutant. Accordingly, the textile can get activated. So, if we know, if we can identify the pollutant. So, IoT based environmental monitoring system. So, we can use like the water pollution. If we IoT based material system, if we can use, then it will monitor the type of pollutants they are present in the water. Accordingly, we can use the suitable filter medium. So, adaptive filtration performance it can change. So, it can change the activity level, or different reactive group can be activated, or maybe it can monitor the pressure drop. So, different types of smart integration can be done within the textile material. So, nanotechnologies are widely used in water pollution control, water filtration system. So, nanoparticles range from 1 to 100 nanometer. So, it is as we increase the nanoparticle, it's at that range it increases the specific surface area, the total surface area per unit volume. And as the specific surface area increases of any particle, its catalytic activity is increased. So, that will help in controlling the water pollution. So, it is used in antimicrobial or photocatalytic textiles. So, it enhances the antimicrobial activity. So, it enhances the adsorption of pollution. So, pollutants it gets adsorbed on the surface by a fiber which is treated with nano material, nanoparticles. And functional coating, there are different types of functional coatings are there, like super hydrophobic treatment is there, antimicrobial treatment. Super hydrophobic treatment, as we have mentioned, that it can adsorb the oil spill from the sea water, or so nanofiber mesh is there, and functional layer and antimicrobial layer. So, this functional coatings are there. So, hydrophobic coating improve oil water separation efficiency. We can remove the oil from water by hydrophobic coating. So, this is the super hydrophobic coating is there, and then antimicrobial coating, okay, which reduces the actually biofouling in the membrane. So, here antimicrobial layer is incorporated, because as the water due to the water filtration. So, whatever bacterial effect will be there on the in the filter structure. So, if we use antimicrobial layer, that will actually reduce the biofouling, and it will enhance its life. So, catalytic coating. So, catalytic coating is also there, which actually enables photodegradation of organic pollutants. So, we use different types of coating, even multiple coating is done within one textile structure, a multi-layer structure. In one layer we can have hydrophobic coating. So, which will have water oil separation, which will enhance the water oil separation efficiency. Then antimicrobial coating, we can do antimicrobial coating. So, that will reduce the biofouling by killing the bacteria there, and then catalytic coating is here, which will enable the photodegradation of organic pollutants. So, different types of treatment, different type of coating treatments can be done for multiple functionality to enhance the water cleaning performance. So, coating thickness may be 10 to 100 nanometer. At that scale we can coat, and now try to see the industrial wastewater treatment. So, textile membranes are used. Initially textile membranes are used to remove the suspended solids and dye. Okay. This different types of membranes used. So, textile based filtration, we can see nanofiber mesh is used, and biotreatment we have done, and then we can use reuse and dewatering we do it. So, that we remove the water and then reuse it. So, flux here is 50 to 200 liter per square meter per hour, this type of water discharge capacity, and used in textile, chemical and food industry. So, this it allows the recycling of industrial water. So, for industrial water recycling, we can use this different types of textile layer. So, oil spill of that is oil spill clean up, we can use textile material as we have already discussed. So, oleophilic, hydrophobic and high absorption. So, that all these different types of layers we can use. So, we can oil absorbing fabric captures hydrocarbon pollutants. So, this captures the hydrocarbon pollutants. So, here oil absorption capacity is typically 20 to 40 gram of oil by per gram of textile material. So, hydrophobic fibers repel water molecules, so that oil can get adsorbed on the surface. So, this is applied in marine pollution control, and these fibers which are used as this fabric can that float on the surface, light fibers are used. So, floating textile barriers. So, marine pollution control, but so this is a floating textile barriers are there. So, what happened in the in place where the oil spill is there. So, what we do, we used to cover that area, contain that area with the textile floating textile material. So, this barrier contains the oil spill. First it will not allow the oil spill to move towards the larger surface. So, it will first try to contain the oil spill within a narrow area, narrow zone, and then the adsorbent fibers capacity is that which capture the hydrocarbons. So, this adsorbent fibers they try to capture after restriction by the floating textile barrier, then we adsorb the hydrocarbons on the fiber surface, which protect the coastal ecosystem, and it is used in offshore drilling site, because in the offshore drilling site where there is always chance of oil spill within that zone, even if there is no accidental oil spill, but in general normal case also there may be some oil spill. So, that zone, that oil drilling site is covered with this type of textile, floating textile material. Now, portable water filter system. This is the portable water filter system, which is actually used to clean the water from if we take the oil reserve like from lake or river, if we take, and this water should be, this filtration system should be able to clean the water to a to drinking water level by removing the different types of bacteria, solid particles like this. So, here we have typically one is pre-filter is there, this is a pre-filter, okay. Then activated carbon layer, this is the activated carbon layer, then antimicrobial layer. So, this multi-layer system is there when we feed water from the top. So, it first pre-filter the coarse particle, then activated carbon which absorbs the organic compound and then removes the bacteria. So, this type of system, finally we get clean water. So, textile membranes are used in portable purification system. So, removes bacteria and suspended particles. Filtration rate typically 1 to 5 liter per minute. So, useful in disaster and relief operation. So, this type of different applications are there. So, textile membranes in desalination. So, for that we also used to remove the salt from water. So, directly from this sea water we can actually use the drinkable water used in membrane. So, membrane system which distill the water. So, it is driven by the vapor pressure, we create the pressure difference. So, this is the relationship here. J is the permeabilization flux through the membrane. So, how much the liquid permeating through the membrane. Cm is the transfer coefficient and P f is the feed side. So, vapor pressure in the feed side and the vapor pressure in the permeate side. So, if we increase the vapor pressure, so the flux will increase, but P f if we increase. So, but if we that if flux is increased, then problem would be that the activity will not be this filtration capacity, filtration performance may be affected. So, it shows that high flux is driven by the vapor pressure difference across the membrane. So, high flux we can achieve, but at the same time we must achieve the filtration efficiency, how much it is actively actually remove the salt from the sea water. So, this type of textile based membranes are used. So, this is used in particularly coastal water treatment plant, where the salt from the sea water is removed and it make the sea water drinkable. So, textile filter in drinking water treatment. So, in remove first the turbidity and pathogen, it removes by textile material can remove, and its filtration efficiency is more than 95% for bacteria. So, the bacterial filtration is there, used in municipal water treatment plant. So, here a nano or micro fiber mesh is used, and functional and antimicrobial treatment is given. So, and then adsorptive material which absorb the organic compound. So, it improves the water clarity and safety also, it improves. So, to make the water drinkable. So, textile based biofiltration systems are also used, which is used to use the bacteria, it uses bacteria on the textile layer, okay, treats air, water and odor naturally, breaks down the volatile organic compound and nutrients. So, biofiltration is there. So, we treat the textile material on biological component. So, textile media support the microbial biofilm. So, on the textile fabric, the biofilm is been actually generated, and where textile material is supporting that. So, volatile organic compound are toxic, carbon based chemicals. So, carbon based chemicals that easily evaporate, and it causes the significant water pollution by contaminating the groundwater and surface water. So, this volatile organic compound has to be removed, and that is the this whatever microorganism is there on the filter, that is biofiltration biofilm which is there, this microorganism it actually degrades the organic pollutants. So, what it break down the volatile organic compound and nutrient. So, that this is the way it filters out the water. So, this is used for wastewater treatment. So, for wastewater treatment, what we understand that we should use the textile base and its biofilm, microbial biofilm is actually created on the textile, and which removes the volatile organic compound, and it is used for wastewater treatment, and it also reduces the BOD and COD level. And whatever we do, we should be actually concerned about our environment. So, biodegradable filtration media was also used. So, natural fibers like cotton we can use for the water filtration. So, it is degradable, and it reduces the environmental waste. Cellulose or chitosan fiber we can use, suitable for eco-friendly filtration system. And now for textile filter, as we have discussed in air filter, in water filter also we can try to reuse the or recycle the filter, so that circular economy is maintained in textile filtration textile also. So, reuse and recycling of filtration material we can use, which reduces the industrial waste, which can extend the life cycle. So, basically if we try to reuse by cleaning, and that system we have to develop, and which promotes the sustainable manufacturing. So, if we try to again the waste, whatever waste from textile filter, we can, if we can bring those waste again into the system, then it will sustainable manufacturing will be promoted. So, life cycle assessment, here we can see we can recycle, extraction is there, manufacturing, then transportation. So, manufacturing, transportation, construction, different operation during use we can do, then recycling, and then after recycling we can extract the fiber and then bring back to its the manufacturing again. So, this life cycle assessment for textile filter is also can be done along with like other materials. So, evaluate the environmental impact from production to disposal. So, what are the different environmental impact that we can evaluate first. So, we can measure the how much energy is consumed and how much energy is emitted, then it supports sustainable product development. So, we have to use different method. We can use life cycle assessment methodology like ISO 14040 method we can adopt. So, membrane fouling in filtration is a very common problem. So, that we can reduce. So, basically the membrane, textile membrane microorganism actually develops on the surface. So, that clogs the membrane pores first. This clogs the membrane pores and reduce the system performance. So, if the pores are clogged, then the liquid flow rate like water flow rate will be reduced and system performance will be deteriorated. So, fouling occurs due to particle accumulation on the membrane. So, that there is a membrane, it has got certain pore size, and on the membrane the particles are getting accumulated. So, this reduces the, as the block they block the pores, this reduces the filtration flux. So, the flux reduction is described by this relationship where J is the flux. So, permeate flux through the membrane or filter. So, applied pressure, delta P is the applied pressure, mu is the fluid viscosity. So, higher viscosity will have lower flux, higher pressure drop will have higher flux, and intrinsic membrane resistance is Rm, and Rf is the fouling resistance due to particle deposition. Now, here this is the there will be some intrinsic resistance of the membrane, but as the fouling is generated, the pores are getting blocked. So, that will enhance the total resistance. So, flux will reduce. So, this is the membrane fouling. So, it explains the flux reduction caused by membrane fouling during filtration. So, this RF is increasing, which reduces the flux. So, now like our in back filter we have discussed that reverse airflow. Similarly, here also we can use in two ways. This is the membrane and particles are developed in one side. So, membrane, this is membrane and here membrane fouling is there. Now, we can use the reverse flow. Reverse flow, there whatever loosely adhered particles are there. So, that those will get cleaned, and also this is called backwashing, and also we can do chemical treatment. So, chemically we can deactivate, remove these particles, that is cleaning method. And now advanced membrane engineering is there. So, developed on the basis of multilayer textile membrane. So, we can use multilayer textile membrane we can develop. So, gradient pore structure improves the efficiency, that is important. So, we can create the textile membrane, multilayer membrane. So, in one membrane, suppose there it is a larger pore size. So, this is having larger pore size, then we can use relatively smaller, then smaller, and so micro. So, that will actually improve the efficiency, because larger particle will be blocked first. So, gradual block gradient actually filtration is there. So, it optimizes the permeability and also filtration efficiency, selectivity. How? So, we can selectively arrest the particle of different sizes. Okay. So, here you can see the larger particle will be on the surface. So, this is used for high performance filtration, where high filtration efficiency is required. Hybrid filtration systems. So, because we can use two technologies, two principles to improve the filtration efficiency. Like textile filter, if we do carbon activated carbon, if we use activated carbon. So, textile filter will be used for say larger particles, and activated carbon will absorb gases or volatile compound. So, combined adsorption, catalysis and membrane filtration, that we can do in a one filter. So, hybrid filtration system we can develop, improve removal of complex pollutants, the different types of mixed pollutants we can address those issues here. So, industrial wastewater treatment, where we do not have any control over the different types of pollutants. So, complex pollutants are there. So, that we can, in those cases we can use this hybrid filtration, where that organic compound will be there, volatile component or particles will be there. So, all these applications we can use where the complex pollutants are present, and it enhances the filtration filter life, and long term filtration efficiency can be maintained. Self cleaning textile material, also it repels and kills the microbes particle. So, photocatalytic coating degrades the component. So, it will kill the microorganism, reduce the membrane fouling, improves the operational lifetime because of the it is not clogged or fouling is reduced. So, that is why clogging will be slower. So, it will improve the life. Often use TiO2 and ZnO2 nanoparticles are used. So, smart environmental monitoring textiles are used to detect the pollutant and environmental condition it detects. It provides real time data on the water or air quality. Integrated sensors connected to the central system, sensors embedded within the textiles detect pollutants in real time connected to digital monitoring system. So, we can in real time we can control the we can monitor the system. So, smart cities we can use, but where we get all the data and relative and based on this data we can activate our filter medium. So, the emerging trends if we see here, so by the development of nano fiber composite membrane is there, which is used widely in water filtration. So, integration of graphene and carbon nanotube material within the textile fiber to enhance its different functionality. Advanced multifunctional textiles are used. So, in the advanced research we give focus on the sustainability. So, the economic aspects are that so textile filters are cheaper than ceramic membrane. So, that is so why do we use textile? So, it is cheaper relatively than other material which is commonly used as ceramic materials are used. So, this production is scalable through industrial spinning process. So, we can use the membrane nanofiber membrane, we can produce nanofiber membrane in industrial scale, lower energy consumption due to high permeability. So, textile membrane is relatively having higher permeability as we have already mentioned. So, lower pressure drop will be there. So, energy cost will be low, and there is a growing textile filter market throughout the globe. So, economically it is sustainable. So, what we have discussed here, let us summarize. So, textile materials provide effective pollution control technologies both for air and water. So, in water treatment textile filters play a great role, particularly nanofiber membrane significantly improve the filtration efficiency by reducing the pressure drop to a great extent. So, we can improve the functionality by functional coating. So, which can remove the different types of pollutants, organic volatile components, different types of components we remove, and also the sustainable materials. So, sustainable materials will dominate because we have to see the how much carbon footprint it is actually generating. So, our process we should always calculate the carbon footprint. So, sustainable process, sustainable material we should use, and this will dominate the future research. So, why should we use textile for filtration? So, that is textile based filtration play a crucial role in environmental protection, both air and water. So, advanced nanotechnology improves the filtration performance. So, nanofiber has been generated. So, it has been developed. So, advanced nanotechnology we can use, or nanoparticle we can nanofiber we can use for filtered medium, or nanoparticle we can incorporate within the textile material to enhance the filtration performance. So, we can integrate the smart system to enhance the pollution monitoring. So, in textile material these are all possible, and also different types of coating we can do, functional coating we can do in the, and textile material is main advantage, it is a flexible, we can it can take any shape. So, flexible, it is not brittle even, it is so, and high strength is relatively high, and continuous research is needed, particularly for sustainable filtration technologies. So, we have discussed the basics of water filtration, what are the different types of fibers required, different types of technologies we can do, how the what will be the sustainable approaches on in the water filtration. And now we will stop this session, and in next session we will discuss in detail of the different types of membrane technologies, how the what are the different types of particles these membranes can arrest, and how the different textile structures been developed to for water pollution control. And also at the towards the end we will discuss different types of studies we have carried out to actually for water pollution control, to make the open surface water to drinkable water without any power. So, that patented technology I will discuss also. So, till then, thank you.